Sorry, guys. Okay, so going through that. There's no height, OH minus is not going to leave. It's not going to be kicked out. It can't be kicked out. It's not going to just spontaneously leave. But a neutral oxygen is a weak acid, a weak base. If you mix a weak base with a strong acid, you can get an acid-base reaction. When you get that, now you're going to have essentially a water bonded to this carbon, right? Water is a weak base, so water can be a leaving group. But if you have a strong nucleophile or a strong base in here, rather than attack the carbon, it's just going to pull one of these acidic protons off. So water, this could also be an alcohol that you protonate. Those can only be leaving groups under really acidic conditions. Okay, so from there, if you had decided no reaction happened, I'll give you a minute to think about what might happen. And I'll answer those questions. So there definitely are beta hydrogens. I think you guys all have that. Strong base or a good nucleophile, I said you can't have that. I didn't explicitly show that you don't have that, right? All we have is sulfuric acid. Sulfuric acid is a strong acid. A strong acid is not going to be a nucleophile or a base. The alcohol, you've got a neutral oxygen, that's a weak base and nucleophile. So you don't have any strong bases or nucleophiles in there. And what this means is, if there's not a strong base or a good nucleophile, this is either going to be E1 or Sn1. Like I said, that strong base, good nucleophile, that's the bifurcation point between the unimolecular mechanisms and the bimolecular mechanisms. You'll go along, if you can just, and I don't want to say it's easy, but if you can figure that out, you go a long way to solving the problem. But it is kind of the trickier, right? Is there a beta hydrogen? Is there a leaving group? It's pretty straightforward. Do you have a good base or a nucleophile is a little subtler. The leaving group's on a secondary carbon. All right, and so so what do we get here? Substitution or an elimination? Anybody got an answer on it? How come?
High temperature.
The what?
High temperature.
High temperature. So this is where we come down to temperature is not as subtle as solvent. Okay? So the solvent effect really just affects the rate. The solvent is rarely, if ever, going to tell you which mechanism happens. The temperature can. So here we've basically decided we're going to get E1 or Sn1, which means a leaving group is going to leave and we're going to get a cation. And then from there, you could get either. All right, but we've given a high temperature. Elimination is favored at high temperature. Say it more properly. Elimination is favored more with increasing temperature. Okay? So as the temperature goes up, you're more likely to get elimination. Here, water is going to leave. This is going to give us carbocation. Actually, I'll just draw it this way, sorry. All right, so water leaves, we get a secondary carbocation. That happens for Sn1 or E1. So now, what's the most likely thing to happen next? It's not substitution or elimination. I'm not turning all the way to my right here, so I'm not always including you. Feel free to answer if you would. All right, yeah.
the H2SO4 donate a proton to carbon?
Nope. So if you want, I see that a lot,
That would be.
right? That's a plus. So if this was a minus, right, it's not going to donate a proton, this would need to be nucleophilic. So this is a strong acid, that's a strong acid. So nothing's going to happen there. The most likely thing to happen is a cation migration, or a hydride migration. Now, you could get the final product. When I finally draw the final product, you could actually get it straight from here. Okay, so let's just do that. Water could grab this proton, make a double bond, get us our alkene. You get cis and trans double bond there. But the other thing that could happen, I'll draw this in red. Crap. All right, so the hydride could migrate. And you get that cation. All right, that hydride, I've talked about hyperconjugation before with you guys. Basically, the CH electrons, that sigma bond, are interacting with the p orbital. That's stable. So the more substituted a carbocation is, the more stable it is. That interaction lets this group move. It could be a hydride that moves, it could be a methyl that moves, it could be an alkyl group that moves. This will give you a benzylic cation. So it's secondary still. They're both secondary cations, but this one's resonance stabilized. And so a lot of students will ask me, like, how do I know if a rearrangement's going to happen? And here's how you know. If a rearrangement can happen to give a more stable cation, it does. Right? There's no sort of, do I need to think about it? Like I said, in this particular case, you could get to the right product without going through that rearrangement. So it would be impossible to tell. And so now, right, we've got water in here. Water takes that proton and gives us the double bond. But like I said, the reason I wanted to put this reaction up was the temperature. The temperature all right, so you should never look at the solvent or temperature first. So I do see this mistake. I think I've slowly realized over the years, these are more kind of subtle things, so I end up talking about it more. There's more different ways it could go. So I end up talking about solvent for like 20 minutes, and you guys are like, solvent's important. Probably shouldn't do that, right? Solvent and temperature are the last things that you should look at. The solvent will kind of give you an idea of rates. Like, could I make this reaction go faster or slower by changing the solvent? Temperature, the only reason temperature is going to become important is if E and S are both possible. So you come to the conclusion, hey, this reaction could be both E1 and Sn1. Based on all the other stuff going on, both of those mechanisms are possible. Now, temperature will tell you which is more favorable. And honestly, these reactions that go through carbocations always tend to be less selective, right? We can get migrations, we can get E1 eliminations, we're going to get a thermodynamic mixture of the products. If you ever need to do an elimination or a substitution reaction in the lab, like you're going to need a product and have to purify that product, you almost always want to make it go E2 or Sn2. Practically speaking, E2 and Sn2 are much better reactions. Sn1 and E1, you're going to make that carbocation. This is now a high energy intermediate, and it can kind of just do all this stuff. So usually when you do E1 or Sn1, often you see, all the possible elimination alkenes. You see some Sn1 product. You might see both. You might see substitution here, and you might see substitution there. It gets very messy. Sn2, it's always a backside attack. E2, it's always a proton that's anticoplanar to the lead. Questions? No. So the problems I put up today, the problem set you have, the substitution and elimination problem set, basically are just a whole bunch of reactions you have to do this, right? And you need to get to where you can do that pretty fast. These questions especially, over here in the upper right, is there a leaving group? Are there beta hydrogens? Strong base, good nucleophile. What kind of carbon is the leaving group on? Those, every time you should be asking that. And that will take you down, like, which mechanism is likely to happen. There's, I think, the other thing on that, the other two problems on that one are, I'm asking you to draw a mechanism for a product, like, I give you everything, and that's typically going to be how it looks on an exam. I'm very rarely going to ask you to predict a product and draw a mechanism, right? It's going to be predict the product, and then another problem. If I ask for a mechanism, I'm going to, like, show you the product. So how do you get there? And then finally, the last problem on that worksheet is judging rates of reaction. And that's, so you were asking about like the stuff you might do, like the worksheets that we had in class. That problem set for chapter 7 is pretty bang on. And we'll do some of that in class. I've kind of done, like, you've seen all the material you're going to see for exam 2 at this point. There's a lot. I actually was debating putting chapter 8 on it and then sat down to, fortunately for you, I do think a little bit. And so I sat down to kind of like list out what was going to be on the exam. Like, okay, that's plenty. All right, I'm done for today. Take off if you need to. If you want to hang around and ask a question, you can. I think there's like 6 videos because I kept